Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenters today are Dr. Corey Packard and Madison Bennett. Dr. Packard is a Principal Engineer and Director of Research and Product Management here at Thermal Analytics. He has more than 20 years of experience in remote sensing and physics-based simulation, with his primary technical focus being EOIR signature prediction. Other technical efforts of Dr. Packard involve field test validations, phenomenological investigations, software development support, and predicting the behavior of optical sensor systems in turbulent atmospheres and from space-based platforms. Madison is a thermal and CFD engineer at Thermal Analytics. Her primary focus is in creation and validation of thermal models for military and commercial use using Titherm, MuSES, and Cotherm. Madison has been with TAI since 2023 when she began as an intern, while obtaining her BS in biomedical engineering from Michigan Technological University. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar, and we'll be sending you the link to view the recording following this presentation. And with that, Corey, if you're...
Sounds good. Thanks, Chris. Welcome, everyone, to today's webinar. We're going to be discussing the simulation of maritime targets and some naval countermeasures with MuSES, and Madison will be helping me present today. Let's get started with the agenda for today's webinar. So during today's webinar, we're going to start with a brief overview of MuSES and then talk a bit about the maritime target model database that can be used with MuSES for the thermal and EOIR simulation of high value targets and maritime scenes. We'll give an update on some feature enhancements that have been made to MuSES specifically for maritime simulations and show some rendering examples to kind of highlight those. Next, we'll discuss the thermal model setup for a frigate example, and we'll show some baseline thermal results. Then we will discuss sea rendering settings, talk about those and their impact on the renderings. We will discuss wake modeling a little bit. Then we will briefly outline how plume simulation can be incorporated. And then we will detail a few different naval countermeasures and show their thermal and EOIR signature impact, and finish with some conclusions.
All right, good morning, everybody. We'll start out with an overview of MuSES. MuSES is a thermal solver and EOIR rendering tool, which takes inputs such as a 3D CAD geometry description, part material thicknesses, thermal properties, and component heat sources. Also taken as input are boundary conditions from environmental sources, such as sun location, the sky and background for radiation exchange, air temperature and wind speed for convective heat transfer, and terrain or sea properties to properly set up the analysis environment. Once these inputs are combined, we get a physical temperature prediction of the target. Each element has a temperature result, and you can graphically see this gradient across the target over the simulation time. Then we can also compute the radiance or apparent temperatures for each element, and from there, images can be rendered from the perspective of a virtual sensor, which can be specular or diffuse, as well as spectral or across a broadband. And we can also get contrast metrics such as delta TRSS and contrast radiance. Throughout TAI's history, we have developed an extensive model database. This includes tracked and wheeled ground vehicles of different uses, airborne targets including jet aircraft, helicopters, and drones, personnel in numerous poses, and as we can see on this slide, simple ship models, cargo ships, sailboats, destroyers, and many other maritime targets to fill our library. Here are a few examples of maritime renderings. We can see in these different renderings the variety of simulation settings that can be applied for maritime modeling. The upper right image shows a littoral scene, so we can view the target at an intersection between land and water. And towards the middle of the screen, we see an image that was rendered in the near infrared at night and shown as a reflection of the moon off the water. We will discuss further some of the other simulation settings shown here throughout this webinar. New features have been added to MuSES that enhance our maritime modeling capabilities. Users can enable and disable solar shadowing. In the picture on the right compared to the left, you can see shadows cast by the ship geometry are visible on the sea surface. This shadow shown is relatively long since the sun is low in the sky at this point. Users can also enable sea surface reflections.
Oh, Madison, sorry to interrupt. Can you
okay.
switch back over to, you're showing the wrong screen currently.
Oh,
Not sure how that happened. There
that
we go.
work?
Perfect, thank you.
Okay,
Yep.
I don't know what happened. Sorry about that. All right. Users can also enable sea surface reflections. The image on the right pictures geometry-induced reflections of the ship that are visible on the sea surface. Water wash can also now be enabled. This represents the thermal impact of spraying water on a ship surface. If we look to the bottom right, we can see some of this effect in the images. In the larger rectangular section of the hull pointed out, we can see the temperature is cooler in the image on the right where water wash was applied compared to the same section in the left image. Similarly, we see this small section below the stack in the left image has cooler temperatures where water wash was applied compared to the same section in the right image. More details on this feature will be discussed later. Now we'll move on to setting up a maritime model using MuSES. We'll need to set up the model environment and can set up a water background for maritime purposes. On the right is our user interface for these settings. Weather can be supplied via a text-based weather file, which contains air temperature, wind speed, and other meteorological parameters. The top image shows where this natural weather file can be selected. Then a water background type is available for both faceted and unfaceted backgrounds. The bottom right image shows the interface where the background settings are selected. Water temperature is able to be specified or calculated here, and simulation methods, solar absorptivity, and surface attenuation can be adjusted. Selecting the paint code option will allow you to change the sea state, which will then change paint parameters based off of the environment wind speed. The example model we are looking at today is the Type 054A frigate. The geometry of this ship is divided into 298 parts and has around 73,000 elements. The parts are grouped into appropriate assemblies and assigned proper attributes like material properties and thickness, convection type and parameters, optical surface properties that are housed within paint codes, imposed heat, and initial conditions. On the right, you can see the ship displayed by different properties. The top image shows the ship colored by convection type, the middle is colored by paint code, and the bottom image displays each part as a unique color. Dynamic inputs are used for the engine state and vessel speed. The engine state is represented as 0 while off, 1 while in idle, and 3 while being exercised. The graph on the left shows the engine state over the length of the simulation, and the graph on the right shows the engine speed over the simulation. The engine is off for 5 minutes, idling for 5 minutes, accelerating for 10 minutes, running at constant speed for 10 minutes, decelerating for 10 minutes, and then idling and off for 10 minutes each. This animation shows the baseline transient thermal results of the frigate model, and you can notice how the thermal results correspond with the engine state across the simulation time. Okay, and now I'll hand it over to Corey.
Thanks, Madison. I'm going to switch the screen presentation here, 1 second. All right, hopefully that's showing up for everybody. Does that look good, Chris?
Yep, looks good.
Excellent. All right, so now that we've discussed the thermal model setup of the frigate, and Madison has shown some baseline transient results through those different engine states and ship speeds, we're going to talk a little bit about the sea settings that were used for rendering purposes here. And the dialog that's shown at the left of this slide shows a subset of the settings that users can supply in terms of specifying what they want the sea to look like. MuSES allows for unstructured seas to be rendered, where the sea radiance is going to vary pixel by pixel, but there are no explicit facets for the geometry that capture waves, just the radiance effect of the waves. But what we're going to look at today is focusing on the structured sea, where there are geometric facets that are generated to represent the sea of choice for the user. As you can see from the settings on the left, users can specify the sea state, the sea spectrum, the spreading angle, wind direction, and importantly, the size and resolution of the sea surface. And we see how the geometry preview can be used at the bottom right of this slide. The specified sea state, size, and the resolution of the sea surface can be previewed there before any renderings are done to kind of fine tune things for the user's application. In addition, solar shadowing and ship reflections, as Madison mentioned, as new features that are in MuSES, those two features can be enabled or disabled if you want to increase accuracy or decrease rendering time. And those are on the dialog in the lower left. In addition to this, users can specify the vertical Z position of the waterline as it intersects the ship. So the waterline of the sea can be adjusted independently of the geometry. So if the loading of the ship is more or less and the waterline would be in different spots, you don't have to make any geometric changes to your model. You can just change the vertical position of the waterline as an independent parameter. Okay, moving on to talk about the wake model a little bit. If signature evaluation is going to be done of moving ships, then to increase the realism, wakes should probably be incorporated. And wakes can be large, they can be detectable from long distances by overhead sensors. And so these can be incorporated into the MuSES structured sea model. And the geometry previews on the right kind of show that, where you see a preview of the structured sea, like I showed on the previous slide, but with a Kelvin wake generated and incorporated into that geometry. And so MuSES's Kelvin wake model, which the parameters are shown via the dialog in the upper right, it uses a description of the watercraft hull and its displacement to create the geometry for that Kelvin wake. And so it adjusts for the ship class, the speed of the ship, moving or stationary. So in this case, because there are times when the ship is stationary and times when it isn't, that wake automatically will look at that ship speed and kind of turn on and off depending on the time that you're doing your rendering at. It also looks at the ship dimensions and its displacement to create that geometry. So changing those parameters in the upper right, and then using that geometry preview will let you see how that geometry is going to change prior to you doing any renderings. Okay, so now we're going to move from wakes to talking about plume modeling a little bit. So MuSES allows users to incorporate plume radiance into EOIR signature renderings. And the way this is done is a CFD analysis is done in an external tool, and the volumetric CFD results from that tool are used to determine the plume signature. And so the output of those CFD tools are things like the temperature distribution in the volume and the gas species concentration in the volume for the different species like CO2, H2O, and soot that are typically present in the plume itself. And then what MuSES does when it's generating its sensor radiometric renderings, it's doing a ray tracing operation from every sensor pixel to the scene. And in the cases where those rays intersect that plume volume, that ray is being traced through the plume volume, and it's calculating not only the atmospheric path from the sensor to the plume, but then the plume radiance from the portion of the ray that goes to the plume itself, as well as the atmospheric impact of the ray on the other side of the plume, and then the background or the ship or whatever hard body is behind that ray at its conclusion. So all that's being incorporated then into the rendering itself, and some examples are shown at right there. So you see in the upper right a battle tank, ground vehicle, an example of an exhaust plume there. The one below that is a passenger craft that's local to our area here. And then the bottom one is an example of a fighter jet with exhaust plumes coming out the back. So now we'll move on to talking about a few different naval countermeasure examples and show how the effectiveness of these countermeasures can be evaluated with MuSES. And the purpose of this is not to make recommendations, but just to show some demonstration examples. And we'll be looking at 3 different countermeasures in today's webinar. The first being ambient exhaust entrainment. The second being the application of water wash to the ship's surface. And the final one being the inclusion of flares. And so we'll have a before and an after version of the frigate to compare so that we can see the impact of each of these 3. First, we'll start with the ambient exhaust entrainment. And the idea here is to cool down the exhaust air prior to exiting the vertical stacks of the ship. And so if you look at the reference geometry shown in the lower right of this slide, you'll see the engines and you'll see 4 different vertical exhaust stacks that come out the top of the ship. The idea here is to mix ambient air forcibly into that exhaust flow so that by the time it exits the top, it's cooler than it would have been otherwise. And because the plume is often quite warm, cooling it before it exits can be a way to really reduce the signature of the ship, especially in the midwave. And so by forcing ambient air into that flow, we can make sure that the exit plume is a bit cooler. And this is kind of diagrammed in the images in the upper right. So you see in the no entrainment example, exhaust flows from those engines going up and out. And then the with entrainment example to the right of that, you can see individual fluid nodes depicted that are being mixed into that stream all along the way as it moves up vertically to create that cooling effect so that the final temperature as it exits would be cooler than that on the right. It will also be higher in velocity because we are creating additional flow rate by forcing this entrainment. So how does this impact what the plume looks like? On this slide, we're taking a look at some cut plane views of the CFD results that were obtained for this. The 2 images on the left with the blue background are fluid temperature results. And again, that's for a single 2D cut plane that's kind of going through the center of the plumes. The 2 images at the right with the dark red background are showing fluid velocity. So if we take a look at the top 2 images, that top row is the no entrainment case. And you could see the fluid temperatures coming out are quite warm. There's a pretty big portion that's that dark red saturation color. That's the high temperature here. Whereas if you look below it in the with entrainment case, you could see the temperatures are certainly cooler. And then if you look at right, you can see that with entrainment, the plume velocities are a bit higher. As you see, the portion that's saturated with that dark red color are a little bit bigger. And that's because of that added velocity that's coming from the forcible entrainment. Also, it might be interesting to point out here that the frontmost stacks are smaller in diameter than the rear stacks, and that's why the velocity is a bit higher in the, as you can see in the upper right image, the front stack has higher velocity than the one behind it, and that's a diameter difference. That's something that shows up in the CFD results and then has an impact on the signature results. So this shows how the fluid temperature and fluid velocity is different with this ambient air entrainment, but what kind of impact does it have on the signature renderings? To figure that out, we're going to use MuSES to incorporate these plumes into our signature renderings and take a look. And so the two images that I'm showing here is the before version of the frigate, which has the standard exhaust plume with no ambient entrainment. The image in the upper left that has the false color palette, that's a radiance image. You can choose to display your results in radiance or apparent temperature, and you can choose from a variety of different color palettes. In this case, I chose kind of a rainbow color pattern for the radiance image and a grayscale palette for the apparent temperature version that's shown below. So the upper image is kind of zoomed in on the stack, so you can see all the pixels that are white there all exceed the saturation limit that we've chosen, in this case being 5 watts per meter squared steradian, and the black and white image below that is zoomed out a little bit farther so you can see that plume in context with the rest of the ship and a little bit the water around it. So that's the before frigate. And if we then take a look at the after frigate, these are all using the same color scale limits on the left hand and right hand images. So we can see that the number of plume pixels on the right that is saturated and above that limit where it would be white is quite a bit fewer pixels than on the left, indicating that it's certainly much cooler, and we see that in the apparent temperature images below as well. So it's difficult to get enough dynamic range to see all the detail on the lower and the high end here, and that's why we've shown it with a couple different scales and zoomed in and out. But we could see that it definitely makes a difference in terms of the plume radiance. And if we want to kind of quantify this difference, there's a few different ways that can be done. One of the ways is using a delta T RSS metric, and I'll explain that briefly. Essentially what that does is it looks at the apparent temperature of the target, the apparent temperature of the background, the standard deviation of target pixels, and it's trying to help describe the average temperature difference between the target and its background. So that can be a way of quantifying the difference in these images in a single number. And so here are two renderings. On the left is the before ship, on the right is the after ship with the ambient entrainment. And you can see the numbers there showing the delta T RSS numbers in apparent temperature units for these two scenarios and this particular view. So that gives you an idea of the signature reduction that can happen with this and how MuSES can be used to quantify this. There are other ways to quantify it, including radiant intensity and contrast radiant intensity and so forth. Okay, so now we'll move on to the next countermeasure. Assuming that this ambient mixing has been done to cool the plume, what might be done in addition to this? So we're going to talk about water wash, and this is another enhancement to MuSES that was made recently. This lets people incorporate the signature management technique, sometimes described as water wash. The idea here is that seawater is being pumped through a series of pipes and then sprayed on the typically the vertical ship surfaces to cloak that underlying surface temperature by trying to mimic the temperature of the surrounding sea. So the more that the side of the ship looks like the surrounding sea, the closer they are in temperature to one another, the smaller the ship appears, and the lower its signature, that delta TRSS number, would get smaller because the average difference is getting smaller. And MuSES lets users include water wash in their thermal simulation, and also include the effects of that in renderings. And so the dialogues at the right show how that can be enabled, and they also show the user inputs. So users can specify initial condition temperatures. They can specify the source of the seawater. In this case, we're using the same water that's being used for the background. We're using that as our upstream part. And you can specify the flow rate in terms of a mass flow rate or volumetric flow rate. And so that's kind of like the rate at which that water can be applied in a variety of different units. So the higher the flow rate, the more likely that surface temperature is going to be close to the seawater temperature. That's its upstream part. The user can also specify the optical surface properties they want to use in the cases where it is wet and the flow rate isn't 0. So this slide shows the thermal impact of water wash. So the two images on the left are the before frigate. So we see on the side of the ship, different colors of yellow and orange. And you can see a little bit warmer spot where the engine is behind that portion of the hull. The image below that with the blue background is the same image, but here we're displaying the sea background with the color itself, so you can get an idea of the temperature difference between the sea and the ship. So these are both thermal images, one with the background just set to white, and the other one where there's a color representing its temperature. And then we see the after on the right, so we're applying a fairly high flow rate in this case. So this is doing an effective job of getting that whole hull surface to be a temperature very close to the sea temperature, which is going to help minimize the overall radiant intensity of the ship. It's going to minimize the portion of the ship that is warmer than the background and reduce its signature. So that's the thermal impact. What about the signature impact? So again, for reference, in the upper left is the before ship temperatures, and below that is a radiance image of the ship. So that's a long wave rendering. And we can see that the delta TRSS is 5 degrees in this case, this particular scenario and view angle. And the after ship, that's reduced down to 3.7. And you can see the hull of the ship there is cooler, and thus its radiance is much closer to that of the surrounding water. The ship reflections that you see in the water are cooler as well. So now we move on to the final countermeasure that we're going to talk about, which is the incorporation of flares into MuSES imagery. So animated flares can be inserted into MuSES animations, and we're doing this by means of a cotherm process. So cotherm is a tool that we developed that allows for the co-simulation of tools, the automation of complex processes. It looks like a block diagram with sort of sequential and concurrent steps. So you can see the flow of information, the flow of control. And so we created a cotherm process to do this flare animation. And what that process assumes is that the flare can be described by a radial distribution of TET elements. They've got a parabolic trajectory that's specified by XYZ velocity components. As you can see by the example that's shown below, we see on the lower left a static image in the midway from a fighter jet with some flares going off, and next to that is an animated version of the same where the sensor is kind of moving in a circle around the jet. And then you can see as the flares are going up and coming down in a parabolic trajectory, they're also drifting backwards because the jet's flying forwards. And these are all user-controlled settings in that cotherm process. It's changing over time. Elements are being added, elements are being removed. This creates the tail. And so with a few different simple cotherm user inputs, we can add those to the ship model as well. And the geometry that you see in the lower right is an example of 2 different times during a transient sequence. The first one where you see two flares on the way up, and then the one below that, you can see those flares already on their way down, and another set of flares on their way up, and these are being fired from the stern of the ship. And so what we'll take a look at next is what this looks like in both the thermal and the infrared. So this slide shows the thermal impact of the flares. On the left, we see the before ship. On the right, we see the after ship. And in this case, we see some flare geometry. They are red, indicating that their physical temperature, greatly exceeds that saturation limit of 100. That temperature is user programmable in the Cotherm process, but it's very much warmer than what's surrounding it. And the idea would be this could be a distraction to potentially an enemy missile or something that's looking for pixels in the scene that are really bright and basically creating a false signature to be deceptive, like a decoy. And so what does this look like in the infrared? So here we see an animation that shows the incorporation of these flares into the simulation. In this animation, which is 10 seconds long, this is 10 frames a second, so there's 100 different renderings that have been stitched together to create this animation. And so the geometry is changing as those flares are going up. The thermal calculations are being done, the renderings are being done. You can see the flares going up and coming down. You can see them, the extreme radiance from those flares reflecting off the horizontal stern of the ship there. You can see the reflections off the water as well. You can see a bit of a Kelvin wake there behind the ship. So we could see all these different elements come together, including a reduced plume temperature by way of that ambient entrainment, a reduced hull signature by way of the water wash that's been applied to the entire hull surface, and then the incorporation of these flares as a distraction technique. So in terms of wrapping up, I think we've shown how MuSES can model high-value maritime targets and do so accurately with realistic sea backgrounds. MuSES has been used in a variety of different maritime validations in the past, and some upcoming ones as well. Madison described some of the recent feature enhancements that have been added to increase the realism of maritime backgrounds and improve contrast calculations and signature management evaluations. We've also discussed a variety of countermeasures like exhaust plume cooling and water wash to minimize the ship's infrared signature, and also showed how flares can be incorporated to create signature distractions to help avoid detection. Finally, we just wanted to mention some of the upcoming defense webinars that we have later this year in case you're interested in some of these other topics. We're going to be doing a multi-part series later this year. The first one being an introduction to MuSES and artificial intelligence and machine learning. So using MuSES imagery for AI ML applications, and then some more specific topics related to that. The first one focusing on UAV, drone systems, and birds, the detection and discrimination of those. Then one on multimodal remote sensing of humans in different cluttered scenes. And then finishing up with overhead persistent infrared, or OPIR, applications for AI ML. So that's the tentative plan for later this year, August through November. And with that, I'll wrap up and say thanks for your attendance and participation, and we'll see what questions maybe have been posted in the chat here.
Yeah, thanks, Corey. Thanks, Madison. I'll open it up to some questions here. What target models do you have for simulation in MuSES?
Yeah, that's a good question. So Madison showed a slide with just a few maritime targets ranging in size from, like a small life raft or a RIB, rigid hull inflatable boat, to fast attack boats, aircraft carriers, cargo ships, frigates, destroyers. But we also have models of other things that that might be in those scenarios as well. Might be a person that's in the water that needs to be rescued, or maybe it's a littoral scene where both the water and the coastline are present in the image. So obviously beyond the maritime targets that we showed, we've got a very large variety of ground vehicles, UAVs, and human personnel. So ground, air, sea, humans, you name it, we've got a lot of targets. But beyond the ones we already have in our database, we also have the ability to create custom targets if what you're looking for is not one that we already have. We've got a team that can create that for you. Good question.
Thank you. Which version of MuSES is needed for water wash?
Yeah, good question. So version 2025.1 that just came out to the public, I believe middle of April this year, is the one that you'll need to have a water wash working as we described in today's webinar. So you're going to want to get the newest release that came out this spring.
Thank you. Is there an own ship view in MuSES when creating scenes?
I'm sorry, can you repeat that, Chris?
Yeah. Is there an own ship view in MuSES when creating scenes?
An own ship view.
OWNSHIP. Maybe we can follow up with that one.
Yeah, maybe we can follow up just to ask a little bit more specifically. I mean, I think Madison showed some screenshots of what typically is visible in MuSES when you're setting up your target model. I mean, if it's just a ship at sea, then typically you're just going to see the ship because the sea is added in during the rendering portion, so you don't see geometry until you get to the rendering process, and then you can use the geometry preview that I showed to see what the size of the sea and the resolution of the sea and how the sea is positioned relative to the ship and all your different sea settings. You know, you can preview that geometry before you do a rendering to see what it's going to look like. But you can also spin that geometry preview around to see it from different angles. But then there's a separate control where you can change the perspective of the sensor to see what you're going to see before you do the rendering. But if that didn't answer it, we can follow up.
All right, thank you. Could you talk more about validation work of ship signature prediction?
Yeah, I could talk a little bit about it. I can't get too specific here, but we've done some validations in the past for a few different U.S. naval groups, and so there's been like at-sea tests that have been done in comparison to MuSES imagery, and we've got some likely upcoming projects in the near future where we'll be doing more of that, but can't get too much more specific on at this time on the call.
Okay, thank you.
We can give more. We can follow up and give more detail if needed with specific people.
Okay, excellent. Let's see. Can you provide a more detailed explanation of the Cothum rule for modeling flares?
Yeah, I can give a little bit more detail, and we've got some slides that go into a bit more detail how it works. But essentially, it looks like a block. The process itself looks like a block diagram with sequential steps, and there's a variety of pieces that are needed. There's a series of steps that go around focusing on creating the geometry that's needed. So for this one, because we used shell elements to represent the flares with a tunable temperature, then to move them up and down in the parabolic manner that we showed, elements have to be added and subtracted for all the different frames of the animation. So there's a part of the process that focuses on manipulating that geometry. So adding elements, deleting elements, and that can all be automated from the command line. So essentially the Cothum process is doing that command line manipulation based on the user's parameters to automatically handle the geometry creation and destruction to create the geometry of the scene that we need. Then there's a sequence that is performing the transient simulations that are needed to predict the temperatures of the flares and the ship and the water background for all the different times. And then finally, there's a third sequence that's doing the renderings using that geometry and the temperatures that have been predicted.
All right, thank you. Let's see. How adaptive is the thermal model of the ship to different environmental factors, and how much time to compute for a new environment?
Yeah, that's a great question. So it's very adaptable to different environments. Users can specify whatever environmental conditions they're interested in, and that's typically supplied via a weather file. So the weather file contains things like air temperature, wind speed, cloud cover, solar loading, if a user wants to specify particular conditions. You know, if you're doing a validation, you can specify particular measured conditions, or you can have the software calculate the transient solar loading and solar positioning for you. I said cloud cover, but there's also sky temperature. So there's a lot of different settings that can be supplied. We've got a variety of those, and new weather files are easy to create. So it's very adaptable to different environments. And as Madison talked about, you could change the ship speed and its heading and the engine state and all those things, and all the different heat rates and flow rates of the model change with that. As far as how long it takes to compute, that's tough to answer because it depends on the complexity of your model. You know, if you've got a life raft, it's different than if you've got a cargo ship, and depends on the computing hardware that you have as well. But in general, it runs pretty quickly. But it is difficult to give a number because it's so dependent on those things, and it's also dependent on how long of a simulation running with how many different time steps, and whether we're talking about renderings or just the thermal. But again, yeah, happy to have a follow-up call and get into more specifics on any of these.
All right, thank you. Is there any thermal interaction between the hull and surrounding sea?
Indeed, there is. Yes. So typically the way that we do it is when we're setting up the thermal model, we are looking at the portion of the hull that is going to be underwater or in contact with the sea surface. And so while the parts of the ship that are above the water line maybe have wind or a similar convection environment applied to them, the portions of the hull that are below the water line are going to have a much higher convection coefficient, and that convection is not going to be with ambient air, but instead it's going to be with the sea temperature itself. So MuSES allows users to specify the sea temperature, or it will calculate it for them with a number of different methods that users can choose. And that specified or calculated sea temperature is used for the convective exchange between the hull and the water background.
All right, thank you. Can you provide some insights into surface-to-surface radiation in Titherm? Seems like there is excessive contribution from solar radiation, even when the weather input file is not very high.
Yeah, I can explain that a little bit.
Value.
Sorry, weather file, what, Chris?
Seems like there's excessive contribution from solar radiation, even when the weather file input value is not very high.
Yeah, okay. Yeah, so I can explain that in general, but sounds like a follow-up call would be useful there. So there is surface-to-surface radiation exchange that's automatically computed by MuSES. So view factors are calculated between all the elements of the scene, all the other elements. It's also computing view factors between all the elements of the ship and the sea surface, as well as the ship and the sky. And so you're getting thermal radiation exchange with the sky, thermal radiation exchange with the water background, and with all the other parts of the ship, because different surfaces that can see each other. In addition to that, if MuSES calculates the solar position and the solar intensity, then depending on your latitude and your longitude and your time zone and time of year and day and all those things, the solar position is being calculated and the strength of the sun is being calculated. So the solar apparent area of all the different elements of the ship is changing as the sun moves in the sky and as its intensity is different, and all that's being taken into account. All the different surfaces depending on the paint code that's applied or the surface condition. They have different albedos and emissivities, and that affects how much solar is absorbed, how much thermal radiation is emitted, and so forth.
Thank you. Can you use water wash for natural sources, i.e. sea state or waves against the hull?
Not at this time. I mean, the basic operation, as I showed, is you can specify the portion of the hull or the ship that you want to apply it to, and you can specify the upstream part and the flow rate. So if you wanted to, I suppose, yeah, you could use that to account for the part of the ship that is maybe above the water line at times, but not always. So you could split your thermal model into the part that's always below the water line and give that a high convection coefficient to the sea surface. And then you could pick some portion of the hull above that that has waves hitting it occasionally. And you could apply a water wash and sort of change the flow rate to mimic some kind of flow rate from the seawater. So yeah, I suppose you could do that, and you could tune the flow rate to mimic like lapping of waves at whatever frequency you're trying to dial in, and then the part above that would just be exposed to the wind.
All right, thank you. Now, what sea model does MuSES use?
Yeah, that's a complicated one to answer in the time that we have here. It's built on kind of a Cox-Monk model, but as I said, there's a lot of details. We've got some other slides, and I think a webinar we did last year went into this in pretty good detail. So I'd maybe reference people back to the webinar that we did last year, or we can follow up with that person and send them a link, because I think we went into detail with a lot of the different things that we didn't cover in today's webinar, since we covered that last year.
All right. Got one more. Any combination of laser energy MNS capabilities with the Maritime MNS solution?
Yeah, okay, interesting question. So MuSES does have some directed energy weapon capabilities. There's maybe two different pieces that I would point out. One of those is what we refer to as laser illumination, and that's where a lower power laser is being aimed at something, maybe for targeting. And in that case, you can incorporate the impact of that laser into renderings. So the reflected laser energy that would come back to the sensor can be incorporated into the rendering. So if you imagine a flat plate and a laser being aimed at it, and some of that laser being reflected back to a sensor that's looking at that flat plate, the power and beam divergence and range and all those things can be specified with the laser. Then that beam profile is then applied to that surface, and the portion that's reflected comes back to the sensor. So that reflected laser radiance is incorporated into the image. The other capability that we have is more of a laser heating, so that would be more of a directed energy weapon, high energy laser scenario, where intense beam profiles can be applied to different parts of a model during the thermal simulation to create the temperature to go up and other effects like that. And did a webinar on that, I think January of 2023, and we'll have a paper coming out on that actually in September, so stay tuned.
Oh, we have one more come through. Is there any tutorial video about what capabilities for aerospace applications MuSES has?
There are some videos, there are some tutorials and website content. So maybe you could indicate in the chat some more specifics about what you're interested in, and we could follow up, because aerospace is a big umbrella.
All right. Well, looks like that will do it for questions. So that will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email later today containing a link to watch the recording of today's webinar session. Again, thank you, and have a nice day. And thanks, Corey, and thanks, Madison.
Thank you, everyone.
Thank you.